An exponential function is a function that can be written as f of x equals some base b to the x power, or you could have y equals b to the x. That's an exponential function. Okay, so the base here has to be positive, and it cannot be equal to 1. So some examples would be like 2 to the x power, or 5 to the 3x plus 1 power, or 2/3 to the x minus 1 power. So as long as this base is positive and we have some type of variable in the power or the exponent, then that is an exponential function. Okay? The base cannot be negative. The base cannot be a variable. So we need to have a positive number as our base, and then we have our variable part in the numerator. All right. Now, we can graph exponential functions. We just have to be careful so that we pick x values that give us points on our graph that would be easy to graph. So for example, let's say that I wanted to graph y equals 3 to the x power. If you've ever heard something is increasing exponentially or decreasing exponentially, that usually means that it's increasing or decreasing pretty fast. Okay, and that's because you'll see if I plug in x equals, and I'm going to do a small table here. If I plug in x equals, say, 1, that's 3 to the first power, or 3. If I plug in x equals 2, that's 3 to the second power, or 9. If I plug in 3, that's 3 to the third power, which is 27. 3 times 3 times 3. So you can see it increases very fast. Just by plugging in x equals 3, I already have 27. Well, you always want to make sure you plug in 0. 3 to the 0 is 1. And then you want to plug in a few negative numbers. I suggest plugging in the same number with just a negative sign as you did the positive. So like -1, -2, -3. Now let's see what that does to this exponential function. If I plug in a -1, then I have y equals 3 to the -1 power. The way that you make that power positive is by moving it to the denominator. So that's 1 over 3 to the first power. That would make the power positive. So when you plug in a -1, you get out a 1/3. Alright, what happens when I plug in a -2? That'll be 3 to the -2 power, or 1 over 3 squared. You make the power positive by moving it to the denominator. So that's 1 over 9. And then what happens when I plug in a -3? That'll be y equals 3 to the -3rd power, or 1 over 3 to the 3rd power, which is 1 over 27. So you see these numbers get really, really small fast. Let's see what that would do to the graph. Okay. I'm going to try to space this out a little bit. It's going to be really hard though, because my numbers get really big really fast with the y's do. So I'm probably not even going to be able to graph this point 327. So I'm going to have to half all these just to get a couple points in. Alright, so I can graph 1, 3, 2, 9, but 327, 3, that's going to be just, way up here somewhere. And then it's going to be really hard to graph these too. 0, 1 is easy to graph, 0, 1. But then these others, -1, 1/3, it's just really hard to graph 1/3 here. That would be about right here. And then -2, 1/9. I mean, that's almost at 0 on the y. And then -3, 1/27. I mean, that's just impossible to graph, really, unless I zoom in my graph. So what happens? This thing takes off pretty quick. Alright, and this side, it just gets closer and closer to the y-axis, but never touches it and never crosses it. It keeps going on and on forever, getting closer and closer forever. Now this is just y equals 3 to the x. If you increase the base, like 4, 5, 6, it's going to increase even faster. Okay? But that's, if you hear something is increasing exponentially, maybe a virus is spreading really fast, exponentially. That is, the virus is increasing or maybe spreading super fast to everybody. The base does not have to be a whole number. Like I showed you up here, the base can be something like 2/3 or some fraction. You need to be careful though if you want to graph a base that's a fraction, because you only want to pick numbers that would give you whole numbers to make the graphing process a little easier. Alright, for example, let's say that I wanted to graph f of x equals 1/2 to the x power. So I want to make sure that the numbers that I pick for x will give me, they don't have to all give me whole numbers, but I want some whole numbers. I want some pretty whole numbers that I can use to graph this thing. So I'm going to show you what happens if I just pick the same numbers. I'm still going to get some fractions, but I can get some whole numbers too. Let's see. So I'm going to say x and y. I'm going to choose -3, -2, -1, 0, 1, 2, and 3. Those points usually, as long as it's not a real complicated number or a complicated function, those usually give you an okay picture of the graph. Alright, so, but what do I have if I plug in a -3? Let's see. I'd have y equals 1/2 to the -3rd power. Alright, so how do I do that? Well, one way that you can do that is you flip the fraction. So you make that 2/1 or just 2, and that'll make the power positive. So that's a little shortcut you can use. If you ever raise a fraction to a negative power, flip the fraction and make the power positive. Alright, so 2 to the 3rd power is 8. So that means when I plug in a -3, I get out a positive 8. Alright, plug in a -2. That's going to give me 2 to the 2nd power, or 4. So when I plug in a -2, I get out a positive 4. plug in a -1. 1/2 to the -1 power, flip, and you get 2 to the first power, or just 2. 1/2 to the 0 power is just 1. 1/2 to the first power is just 1/2. 1/2 to the second power, that means 1/2 times 1/2, or 1/4. 1/2 to the third power, 1/2 times 1/2 times 1/2, that's 1/8. Alright, so you can see as these numbers get larger and larger, the y gets smaller and smaller. Let's see what that would look like graphed. Alright, -3, 8. So -3, 8 is here. -2, 4. -1, 2. 0, 1. Now here's where they start getting a little tougher to graph. 1, 1/2. So 1/2 other way. 2, 1/4. So that's closer to the x-axis. 3, 1/8. So that's even closer to the x-axis. So this graph goes through these points. It goes down, down, down. And then it gets closer and closer to the x-axis, but never touches. Okay. Alright, so we can actually use a graph like this. This graph here is right here, y equals 1/2 to the x power. We could use this graph here to graph something like this. Y equals 1/2 to the x plus 1 power. Okay? That plus 1 is going to take and shift every point on my graph over 1 unit. You would think to the right, but it's not to the right, it's to the left. So if you add something in the power up here, that will shift, or that shifts every point to the left 1 unit. Alright, just the opposite of what you would probably think. Okay? So if I was given this graph, then I could sketch this graph really quick by just shifting every point to the left 1 unit. Alright, so you see this point right here, if I just shifted it to the left 1 unit, if I took this one and shifted it to the left, took this one and shifted it to the left, this one shifted it to the left, and did that with every point. And this graph here would be y equals 1/2 to the x plus 1. Now what do you think happens if I subtract 1? Usually with subtraction you may think left, but it would just take every point of y equals x, or 1/2 to the x. It'd take that and shift everything to the right. Okay, so if you have plus in the power, you shift that many units to the left. If you have minus in the power, you shift that many units to the right. Again, it's probably the opposite of what you would think, but that's the way that it works out. Now, if we said adding to the exponent shifts the graph to the left, and subtracting to the exponent shifts the graph to the right, what do you think adding to the function would do? So for example, if I have f of x equals 3 to the x and then plus 1 right here, when you add to the function itself, that's going to shift the graph up that many units. So adding to the function shifts the graph up. Subtracting from the function then shifts the graph down that many units. So look at this graph I have here. This is the graph f of x equals 2 to the x power. Using this given graph, I can graph g of x and h of x pretty quick. Alright, to graph g of x, if I let g of x equal 2 to the x plus 2 power, then all I would need to do is take this graph here, 2 to the x. Since I have a plus 2 here, I would just shift every point to the left 2. So this point that's at 3, x equals 3, I would shift that over 2 units. This point that's at x equals 2, shift that over 2 units. This one, shift it over 2 units. Shift this one over 2 units and do the same with these. Shift this one over 2 units, this one over 2 units, and this one over 2 units. Alright. So now this red graph here, that would be g of x equals 2 to the x plus 2 power. Okay. Can also graph h pretty quick. If I take my graph f of x equals 2 to the x, this graph, then I can shift it to the right, or no, I'm sorry, shift it, since it's minus 1 from the exponential, you shift it down 1 unit. So from this black graph here, every point just shift it down 1 unit. Okay. So now this blue graph here, that's h of x equals 2 to the x minus 1. Okay. So that's exponential functions. We have one special exponential function that I want to cover now, and its base, it's called the natural base, and it is e. Say e is not a number, it's a letter. Well, e is called the natural base. It applies in most of the time if we're dealing with exponential functions. Growth and decay, maybe a population, of spread of a disease, of maybe the growth of, say, some type of animal, or the extinction of some type of animal. A lot of times the natural base e is used. Alright, e is the same type of number as pi. It's called a transcendental number because it's actually just a symbol that stands for a number. Alright, e is approximately 2.71881827, and it just keeps going on and on forever, and it never forms a pattern, just like pi. Okay, so think of e as pi in a way. It's not used the same way, but it's kind of like pi. Okay, and the function, the basic e function that we use is e to the x power. That's an exponential function. It's also a transcendental function. Okay, but if we have e to some power, then if you've noticed on some calculators, we have sometimes an e to the x button. I don't see one on this calculator, but we also have an ln button, which we'll get into. That is a special form of e. Okay, but a lot of calculators, not this one here, will have an e to the x button. Okay, and so if we put in powers for x, you could graph e to the x, right? Because e is this number right here. Now, in physics and other classes, usually we approximate e as 2.72. You know, it's not the same, but it's really close to that. Just like we approximate pi as 3.14, e is about 2.72. Okay. All right.